Hello, welcome back to the wonderful world of astronomy. This is Chapter 18, The Bizarre Stellar Graveyard, Part 3 on my favorite topic in astronomy, black holes. First, a review question, thinking over things we learned back in Chapter 17 and at the beginning of Chapter 18. At the end of a high-mass star's life, after its core becomes iron, it explodes in an event known as a what? A supernova. At the end of a high-mass star's life, the core that is left behind becomes which of the following? Two of the following are possible. A neutron star and a black hole. And in the previous video, you learned about neutron stars. And now we're going to look at when the highest mass stars, when they come to the end of their life, the core becomes a black hole. So the big picture, at the end of the lives of stars, low and intermediate mass stars become white dwarfs, and high mass stars become neutron stars or black holes. And remember that probably about 96% of stars will become white dwarfs. So by far the majority will become white dwarfs. Very small minority, about 4% become neutron stars or black holes, and a very small fraction of those actually become black holes. A black hole is an object whose gravity is so powerful that not even light can escape it. This is a slide from back in Chapter 4 when you learned about gravity. And I told you about, based on the mass of the Earth, its gravitational pull, and the size of the Earth, it takes a certain speed to be able to get away from its surface. And to get away, I don't mean like when we kick a football up into the air, that doesn't have to be going that fast. But escape speed means to be going so fast that you actually can escape from the gravitational pull of the planet Earth. And so when we want to send rockets to other planets, they have to be going at least this speed. So the escape speed from Earth is 11.2 kilometers per second. And I gave you this equation, and just look at what it's based on. There is G, which is the universal gravitational constant, which defines how strong gravity is throughout the universe. And it's based on the mass of the planet. And we're dividing by the radius of the planet. And actually, we can more generally think of that as how far you are from the center when you want to have this escape speed. But if you're on the surface, that's going to be the radius of the planet. A black hole has an escape speed much greater than Earth's escape speed. In fact, the escape speed is the speed of light, 3 × 10⁸ meters per second. It is possible to get close enough to a black hole that escape speed is the speed of light. And I have this chart down here reminding you of, from back in Chapter 4, Isaac Newton's law of gravitation. The idea is that any two objects in the universe will attract each other with a force of gravity that is that universal constant times the product of the masses divided by distance squared. And here I want to focus on that divided by distance squared. So the closer objects get to each other, because it's a larger number in the denominator, the force of gravity gets larger. And because a black hole is very, very small, it's a lot of mass, several times the mass of the sun, but it's very, very small, it's possible to get close enough to it to where the gravitational force is overwhelming and you can't get away. The anatomy of a black hole, 2 parts I'd like you to know. The first part is the center of it, the singularity. The singularity is the center of the black hole where matter is infinitely dense. So it's thought that when a very high mass star collapses, all of its mass goes down to this single point of 0 size, but it's still all the mass. So that's what we mean by it's infinitely dense. That's the singularity. The other part of the black hole is the event horizon. It's not really a physical thing, it's more a boundary. The event horizon is the boundary around a black hole where escape speed is the speed of light. We consider it the point of no return. So imagine you're in a spaceship and you're flying out here. You might be in orbit around the black hole. And depending on how close you get, it might be a strong gravitational pull, but if you've got rockets strong enough, you have at least the potential to fly away to get away from it. But once you cross this boundary, you're not getting out because the escape speed is the speed of light and nothing can travel at the speed of light. Light itself can travel at the speed of light, but you go farther in and not even light can escape. So think of the event horizon as the boundary of no return. Let's talk about the singularity. Beyond the neutron star limit, which is about 3 solar masses, no known force can resist the crush of gravity. So think back to when a high mass star explodes in a supernova, it blows off its outer layers, and the core collapses down to a ball of neutrons. So that core is iron and then it collapses down to a ball of neutrons. And it is neutron degeneracy pressure that holds up that ball of neutrons against gravity. Well, if this thing has a very high mass, about more than 3 solar masses, then the neutron degeneracy pressure cannot hold up against gravity, and this thing will just crush down to 0 size. We don't know of any force in nature that will kick in and stop it from being crushed down. So we believe it crushes down to 0 size. Now, this is all speculative. It's just based on that we don't know of any forces that would kick in. But at the very least, we do know that it would crush down to a very, very small size. And we do see black holes out there in the galaxy. So whether or not it actually crushes down to 0 size or not, we don't know. Our laws of physics aren't that developed yet because we have no observational or experimental evidence that would lead to a theory. According to the general theory of relativity that Einstein published in 1915, gravity crushes all the matter into a single point known as the singularity. However, later in the 20th century, in about the 1920s, quantum mechanics or quantum physics developed, and quantum physics predicts a different scenario near the center of the black hole. Quantum physics says that it does not crush down to 0 size. So when we think about the inside of a black hole, general theory of relativity says one thing, quantum mechanics says another thing. So basically, we need new physics to figure out exactly what's going on. But the standard picture that we teach and that's been taught since at least the 1950s and 60s has been that it goes down to 0 size, and that's called a singularity. The surface of a black hole, notice I put that in quotes, kind of like I put in quotes the surface of the sun, the photosphere, back in chapter 14. The surface of a black hole is the radius at which the escape velocity equals the speed of light. So we're talking about the event horizon. It's a spherical surface, that event horizon. The radius of that sphere, so going out to the event horizon, is known as the Schwarzschild radius. So we just have a specific name for the radius of a black hole, and it's called the Schwarzschild radius. So when we talk about the size of a black hole, keep in mind there's 2 different things we might be talking about. The singularity at the center, that has 0 size. But generally when we think about the hole in space, the black hole, we're talking about the Schwarzschild radius, the radius of the event horizon. As I mentioned earlier, neutron degeneracy pressure can no longer support a neutron star against gravity if its mass exceeds 3 solar masses, and some massive star supernovae can make a black hole if enough mass falls onto the core. And let's talk about the size of the black hole versus the mass of the black hole. When mass is added to a black hole, the black hole's size increases. It's a pretty simple formula if you want to know how large is the Schwarzschild radius of a black hole. You take its mass in solar masses, so how many times it is the mass of the sun, multiply by 6, and that's its diameter in kilometers. So for example, if you have a black hole with 5 solar masses, and that would be a pretty typical mass of a black hole, multiply that by 6, and so its diameter is 30 kilometers, or about 19 miles across. Now, there are some black holes known as supermassive black holes. These are black holes found at the center of galaxies that can be millions or billions of solar masses. So let's consider a supermassive black hole with 1.5 billion solar masses. If we do the math, you multiply it by 6, you get so many kilometers, and then I've done a conversion to astronomical units here, but it would be the size of Neptune's orbit around the sun. It would have a diameter of about 30 astronomical units. So when we talk about these supermassive black holes, such as the one that's at the center of our galaxy, these have a size comparable to our solar system. Decades before the discovery of black holes, Albert Einstein was working out his general theory of relativity, in which he described mathematically the nature of space and time, which we call space-time, and gravity. And it predicted the existence of black holes. And often when thinking about space-time and how mass affects space-time, we use this rubber sheet analogy. So you can see these 3 pictures of rubber sheets, and in the middle you can see putting a ball in the center and how it warps the rubber sheet. And that's an analogy to how mass warps space-time around it. If the sun were to become a black hole, its gravity would be different only near the event horizon. Not that the sun would become a black hole, because it's only got 1 solar mass and you need at least 3 solar masses to do that. But if it did, or if any star did become a black hole, gravity would only change substantially near the event horizon, meaning, I bring up in this slide, if the sun were to become a black hole. Let's say the sun became a black hole. Earth would continue orbiting around the sun. The sun, this new black hole, wouldn't just suck in all the planets that are in orbit around it. Earth would orbit around it just as it orbits around the sun. Now, it would be a very dark sky and it would be cold because we wouldn't have a sun anymore. But what I'm getting at here is that Earth would continue orbiting around this black hole. You can look at these pictures here. The first one, it says a 2-dimensional representation of flat space-time. Each pair of circles is separated by the same radial distance. And then we put a mass in the middle. We can say this could be a star, it could be a planet, a neutron star, whatever. The way a mass affects the rubber sheet is similar to the way gravity curves space-time. The circles become more widely separated, indicating greater curvature as we move closer to the mass. And then C represents, we put in our rubber sheet a very small yet highly massive, so a very dense marble, and we drop it in and it just sinks way down to the bottom, stretching that rubber sheet. It says the curvature of space-time becomes greater and greater as we approach a black hole, and a black hole itself is like a bottomless pit in space. So the event horizon is here, and if you imagine, if you had a rubber sheet, and on any of these 2 ones to the left, you pluck a marble, and the marble would represent some object, maybe a rocket or a planet, whatever, and it might go in orbit, or it might just fly off like this. But the idea here is that if you had a marble way down here where my pointer is, there's no amount of energy you can pluck it with to get it to come out of the event horizon. Near the black hole, space-time is significantly warped. Straight lines are not straight. Space and time are curved. And this actually has been experimentally and observationally verified, not that we are anywhere near a black hole, but we do see space-time being warped around the Earth and around the sun and around different planets. A black hole's mass strongly warps space and time, or I just used the one word space-time, in the vicinity of its event horizon. There are some strange effects that Einstein's general theory of relativity predicts would happen near a black hole. And again, the practical of this isn't just about black holes. This is actually about any mass, such as the sun or the earth. And on very small levels, we have observed this experimentally about regarding the gravitational field of the earth. It's just going to be much more pronounced near a black hole. So time passes more slowly near the event horizon. And if you saw the movie Interstellar, there's one scene where it's a good example of that, where time passes differently for the different people that were on this space mission. So for example, a rocket ship that's far away from the black hole yet orbiting around, there might be 50 minutes that go by. And for people in the rocket ship closer to the black hole, only 15 minutes might go by. So their time actually flows by at a slower rate. And the closer to the black hole you get, the more slowed down time is. So that in fact, if you were to get right at the event horizon, time would be infinitely slowed down for you. Another interesting effect near black holes, and again, nothing special about black holes there, this is just what gravity does, is tidal forces. Now, remember back to chapter 4 when we were studying gravity, this is actually what causes the tides on Earth. It's the gravitational pull of the moon on the water on the Earth. Well, when you get close to a black hole, everything is more pronounced. Gravity is much stronger. So we have this picture of this unfortunate astronaut who's going down into, almost going into the event horizon, and he is being stretched and squeezed by tidal forces because the force of gravity on his feet is much stronger than the force of gravity on his torso, much stronger than the force of gravity on his hands. So he'll actually be stretched out. He'll be spaghettified. That's the word we use in astrophysics, spaghettified. Tidal forces near the event horizon of a 3 solar mass black hole would be lethal to humans. Tidal forces would be gentler near a supermassive black hole because its radius is much bigger. So in fact, if you went near what I'll call a normal size black hole, maybe 3 or 10 solar masses, then you would be stretched with millions of ton differential force between your top and your bottom. However, if you were to enter a supermassive black hole, which is roughly the size of our solar system, there isn't that much appreciable difference of forces between your feet and your head, and in fact you wouldn't even notice if you entered. This is a simulation of a star being devoured by a black hole by tidal forces. So astronomers have seen this up in space where a star gets too close to a black hole and it starts to get spaghettified. And in this simulation, it forms into an accretion disk as it's swirling down the drain, going into a smaller and smaller area, trying to get into the black hole. I want to talk now about how we discover black holes. Here you see an illustration of a star, and it's usually going to be a giant or a supergiant star. Just like when you saw my video on white dwarfs, or when you saw my lesson on white dwarfs and neutron stars, it tends to be a large star that has grown from being a main sequence, and it loses gravitational force on its outer layers, although it doesn't have to be a giant star. But what happens is these outer layers are more strongly attracted to the black hole than they are to it. And it says here in the illustration, a compact companion. So when black holes were first discovered, astronomers would see stuff like this. We would see a star, and it's not stationary like on this slide. It's going around in orbit, and they were looking for what is it orbiting around. And normally when you see a star in orbit, it's around another star. But in this case, it was around nothing. So something with a lot of mass to keep the star in orbit, but not giving off too much light. And then on further investigation, they found, well, actually, it's a strong source of X-rays, not visible light, but X-rays, and that was coming from the accretion disk. So the giant star loses its outer layers. Those outer layers fall onto the accretion disk, and the accretion disk heats up very hot. We measure a black hole's mass by using the orbital properties of a companion star. So not all black holes are going to have a companion star. And if they don't, if you just have a lone black hole that's out there in space, it's going to be very difficult to even to detect it without seeing its effect on something else. So we tend to find them going around a companion star. We measure the velocity and distance of the gas that's going around it, and we can use this to figure out the mass of the black hole. A black hole will be very massive. It's going to be at least 3 solar masses. And a black hole should have an accretion disk with very high temperature, typically about 1,000,000 Kelvin, as all that gas is it's competing to get into a smaller and smaller space, and it heats up with a lot of friction. And at 1,000,000 Kelvin, it emits a lot of X-rays. So black holes tend to be X-ray emitters. The first black hole discovered was in the 1960s. It was called Cygnus X1. The X refers to that it was an X-ray source. This is a painting of it. In the upper left hand, you can see where Cygnus X1 is in the constellation Cygnus. And this is a painting of it. The idea is that there's a giant blue star and its gas is falling onto the black hole. We have the very bright hot accretion disk giving off X-rays, and then notice that black hole in the center from which no light is escaping. So some X-ray binaries contain compact object of mass exceeding 3 solar masses, which are likely to be black holes. And remember what a binary is. Binary just means that there are 2 objects, 2 stars, to whatever they are, but orbiting around each other. One famous X-ray binary, as I said, the first one discovered with a black hole is in the constellation Cygnus. A few years ago, astronomers got the first image of a black hole, and it is inside the center of this galaxy M87. M87 is about 55 million light years away. And astronomers were able to look through all the stars and gas that are inside this galaxy, peer into that bright center, and get an image of a black hole. It's a supermassive black hole. And here is one of the first images of that black hole. Now, it's not a very high resolution image, but considering first of all, it's the first one in existence, so that's a pretty good feat that they got it at all. And also considering that they're looking through 55 million light years of space, looking into the center of another galaxy, it's very amazing that they were able to get this. What you see, first of all, is a dark center, and that's the event horizon. And then the bright area around it is the accretion disk, glowing very hot. This one here, a cartoon overlaid on it, you can see a size comparison of the M87 black hole and our solar system. So you can see the size of our solar system. There's Pluto's orbit, and at the time that this cartoon was made a few years ago, that's where Voyager 1 was. And so the cartoonist just wanted to show that this event horizon is about as big as our longest traveled spaceship has been. M87's black hole is a particularly supermassive one. It has a mass of about 6 billion solar masses. And this image came out a couple years later. It's an image of the black hole at the Milky Way galaxy's center. And we've known for a while, say a couple of decades, that there is a black hole at the center of our galaxy. In fact, there's a black hole at the center of most large galaxies. But this is one of the first pictures of it. It looks very similar to the other one. And that concludes our lesson on black holes. So what have we learned? What is a black hole? A black hole is a massive object whose radius is so small that the escape velocity exceeds the speed of light. Black holes are formed from the collapse of a high mass star. The main parts of a black hole are its singularity and its event horizon. What would it be like to visit a black hole? Very strange. As space and time are warped around a black hole. Now, first of all, you can orbit a black hole like any other object of the same mass. So black holes don't suck things in. So as long as you're at a safe distance, you can orbit around just fine, just like you orbit around a star. You could orbit around a planet. But near the event horizon, time slows down and tidal forces are very strong. And that concludes Chapter 18, The Bizarre Stellar Graveyard. Have a great day.